Hello, my name is Matthew Thornton, and I will be giving a short presentation on the simple harmonic oscillator. I chose the pendulum instead of like a mast on the end of a spring because I feel that this phenomena I can apply to everyday life in situations that I would be in. I mean, I can apply the mass on a spring, but today we're going to be talking about the pendulum. If you can imagine, there is a string that's attached to some point. At the end of it is a weighted object, let's say a ball, a sphere, and it wants to stay in equilibrium right here. You pull it back at an angle of theta and you let go. The time it takes for this ball to swing past its equilibrium and come back to the same spot, that's the period. So, this is the length, that is theta, and then this is like the mass times gravity. Now, this is sort of the force that's going on. We have the tension of the string and the mass times gravity, or the other one known as the weight, go downwards. But that doesn't really give you the the calculation. Like there are a lot of different things that cancel out. Like that's what I thought was pretty cool about this phenomena is that if you have two different pendulums that have the same length string, one ball is a lot heavier than the other one, and you let go at the same theta, they'll both come back at the same time. The period will be the same. And if you pull one ball further back, theta was longer than the second pendulum, they would still have about the same period. No matter how far you're back, no matter what the changes of weight. The only thing that really changes the period is the length of the string. So the calculation for finding the time would be the period equals 2 pi times the square root of the length over g. Now, g is 9.8 meters per second, and pi is 3.14. If you pull pi inside of the 2 pi into the square root, you would square 2, so that's 4, and pi would become approximately 9.8. So you can cancel the 9.8 on both the numerator and the denominator and end up with the period equals the square root of 4 times the length. And so if you square both sides, divide by 4, you can get the length by taking the average time it takes for the period squared divided by 4. So let's say you're camping or something and you had this tree that you wanted to figure out, and all you had was a little rope on you and a rock. You can throw that rock over the branch, get it to a spot where you can swing it and it's not going to change the length. It would be beneficial to do about 10 oscillations. Take the average by dividing it by 10, and you just take that time in seconds, square it, and divide it by 4. You get the exact length in meters. Not exact, because in this calculation, which I'm not going to go over, you're using theta, or you're using the sine of theta in this equation. So a lot of things cancel out, but the true, if you really wanted to get the length of how long it takes, theta is actually the rounded, like the circumference of the circle, like a part of the circumference of a circle, and sine of theta is actually the line between the 2 points. So the shorter the angle, you want to stay within like 20 degrees. The shorter the angle, this length is very close to that, but if it was like 90 degrees, this length is going to be a lot longer than straight across. So the accuracy is lost the further away, the further the angle theta. So yeah, that's a simple harmonic pendulum, and you can use it in everyday life. Thanks.